be presenting our paper entitled Enhanced Sensorless Predictive Direct Power Control for PWM Rectifier with Constant Switching Frequency under Grid Disturbances. The circuit shows the structure of a PWM rectifier. By appropriately switching the IGBTs, we can have controllable DC voltage, controllable power factor, and sinusoidal line current with low harmonics. The switching of the IGBTs is made through a control circuit. We develop a control strategy that will determine the most appropriate switching state that will take us from the current state into the desired state of the rectifier. The desired state would be the DC voltage level and the power factor, which is usually set to unity. For the current state, we must measure the line voltages, line currents, and DC voltage, with an overall of 5 to 7 sensors. Sensors are expensive, they are heavy, and they could be a source of errors. Reducing the number of sensors means that our system will be lower in cost, smaller in volume, and less affected by noise. We'll be attempting to remove the line voltage sensors. If we look at the structure of a PWM rectifier, we can see that the line voltages are related to other parameters that are known to us. We have sensors for the line current and the DC voltage, and we're already familiar with the operating switching state. But the expression has a derivative in it. So, when we want to get rid of the derivative, we resort to integration. But, by Faraday's law, we know that the integral of the line voltage gives us flux. The flux doesn't really exist, and so what we will be estimating is called virtual flux. Now, luckily, if we assume that our network is balanced, we can deduce the line voltages directly from the estimated flux. The flux expression has a pure integration in it. Now, this could be troublesome because pure integrators are often known for their DC offsets and high sensitivity to grid disturbances. So to go around that again, we use second-order generalized integrators, or just SOGI. Now, briefly, what SOGI does is that it takes the signal that we want to integrate, filters it out from all unwanted component, then it performs the integration. And again, we're faced with another problem. SOGI requires prior knowledge of grid frequency. This means that our voltage estimation will be inaccurate, say in case of frequency oscillations of the grid, or maybe if you want to take the system from a 50 Hz network and try to operate it at a 60 Hz network. So we need to do something about that. For this, we used frequency locked loop, or FLL. FLL takes signals from different stages of SOGI in order to determine the discrepancy in the grid frequency, and then uses an integral regulator to compensate for this error. Finally, we can remove the line voltage sensors and replace them with a line voltage estimator, which then brings us to the control strategy, or in other words, how are we going to determine the best switching state to execute. For this, we have used Model Predictive Direct Power Control. In this, we use mathematical modeling of the rectifier in order to predict the powers at the next sampling instant. We do this for all possible switching states. It is called Finite Control set because there only exist 8 possible switching patterns. Then, we describe our desired performance as a cost function to be minimized. In this case, we want to minimize the error between the predicted and the reference powers. Then we calculate the cost function for each state individually, compare the cost functions generated, and pick up the switching state that generates the smallest cost function, that is, the smallest error. But in this, we have no say over the switching frequency because each sampling period we are generating a new state and it might not be as the previous, so we're left with variable switching frequency. Now, What we proposed to solve this is to not execute the switching state directly. Instead, we use it to deduce the converter voltage and then use space vector modulation to generate the switching states at a constant switching frequency of our choice. So this block diagram shows the overall control circuit of PWM rectifier. The reference active power is generated by PI controller from the reference DC voltage. The reference reactive power is set freely. We set it to 0 when we want to operate at unity power factor. The next instant powers are predicted for all possible switching states, and then cost function is minimized in order to obtain the reference converter voltage, which is then fed to space vector modulator in order to generate the switching states. The previous block diagram was implemented in MATLAB Simulink in order to check the rectifier's performance under one-step change in the DC voltage and two-step changes in the reference reactive power. For the first part, we have tested it under ideal network with no FL. The results were as follows. We had good regulation of the DC voltage. The rectifier smoothly moved from lagging power factor to unity to leading, and the line current was kept sinusoidal through the whole operation with low harmonic content. In the second part, we tried it with distorted network with frequency fluctuations. The results this time has turned into complete chaos. Now we try to see the effect of FLL on the circuit, keeping the same distorted network with frequency fluctuations. Just by eye inspection, we can see the huge improvement that FLL brings to the table. Now, naturally, the waveforms are not as good as that of ideal network. DC voltage and the active power ripples, as well as the line current distortions, have increased, but all within a tolerable range given the amount of disturbance injected into the network. So in light of what has been presented previously, you could come up to two main conclusions. The first is that the proposed strategy is indeed effective and that it solves the variable switching frequency associated with finite control set predictive control. The second is that the combination of sensorless control with frequency locked loop makes the rectifier less sensitive to grid disturbances. However, we still have some limitations. One is that we had to assume a balanced network in order to be able to estimate the voltage. The second is that as we're adding more components into the control scheme, such as SOGI, FLL, space vector modulation, we're making it more complex and we're increasing computational burden. Last but not least is that the control over the power factor is not really precise. We can set the reactive power to any value that we want, but should the DC level reference change or the load, the power factor will also change. So in future work, we'll be trying to work these problems.